the question came up in my class also, then in OSX class of the question. Suppose you have some observable O. And taking this average, right? Or something like OI, E of OI. So this I said it is, so this is equal to this average, where this average is taken over noise or randomness or whatever is there in the whatever randomness is there in the problem. Okay? Is it okay? Let's, I said I forgot what was the observable here. There is some integral like that, right? And then I wrote it as, I think that the Laplace transform, e to the power minus st t of t dt where t goes from 0 to infinity, so that I wrote it as e to the power minus s t and this average is over noise, where t again I express as a function of the noise, right? And then OSX class also I think we had something like that. So then I said that okay, it's because the randomness is only there in the problem, so that's what randomness. But probably that was not a very good answer. Right? So is it okay, or do you know why this is equal to that? Or it's maybe it's trivial. I don't know. It's quite logical, right? Yeah. But let me just make it a bit rigorous. It's logical actually, it's quite logical. But let's, this is the definition of average, but I am saying why these two are equivalent. So this is, suppose the distribution of O is given. So this average is taken, there is nothing randomness here on the left hand side. Because this is P of O is given, then you are multiplying O with P of O and then, or in the discrete case you are just multiplying O with P of O and then summing over O. And right hand side you are putting O and averaging over the noises, suppose.
Because the noise, in the evolution equation.
Yeah, a noise or whatever randomness is there in the system. It's fine, right? Or it's not? It's okay, right? Or is it clear? So this left hand side is a definition of the average, but the right hand side average I am taking with respect to the randomness in the system, and left hand side average I am taking with respect to the distribution of the. But my question is that it is nothing to do with equilibrium. My answer is that it is nothing to do with equilibrium. Whatever the randomness or whatever the problem, it is true always.
No, wait, the left hand side is the definition of average.
Left hand side is the definition of average.
And you write
so left hand side, let me call it O average. O bar. So left hand side, let me call it O bar. And right hand side, I am taking this average with respect to the random variables in the system.
So what is the expression for that?
So O I can express in terms of some. So when I take this average, O I express as a function of the random variables in the system, right? So this is in fact how you do simulations. In fact, it doesn't assume your algorithmicity because actually it doesn't have to be algorithmic in the system. Yeah, maybe it come out, but let me just. As I want to show that this average is same as this average, right? Suppose there is no temperature also in the system. It's some random variables in the problem. Doesn't matter. It might be just a path of a random path or something. There is no temperature. It's just path goes past and something. How do you evaluate this one? Suppose you are doing a simulation. So O is a function of randomness in the system, right? So if you take one realization of randomness, you will get one O. If you take another realization of randomness, you will get another O. For example, you O me with a n point, O me with a position of a random marker after n steps. So if you take one noise realization, you will get one O. If you take one another noise realization, you will get another O, right? So how are you going to evaluate this? Suppose you are doing this equation. Just pick up a one realization of randomness and evaluate O. We can O has an expression in terms of the randomness, so you just evaluate O and just keep it, and then take another realization of randomness, evaluate O and keep it. So what you are doing is actually 1 to R. So where R denotes the realizations, right? And let me just call it O of I. So this is the value of O in the ith realization, right? So you will just draw, for example, in the random walk case, you will just draw the sequence of etas and add them up, and that will give you 1. Right? So it's true for any. This is how you do. This is how you evaluate averages when you do a simulation, right? Yeah. So now let's look at this one here. So suppose R is very large. Let's for a time being consider this discrete. You can just straightforwardly go to the counting. Suppose R is very large. So there will be lots of realizations. You will get the same value of O, right? So let's group them up like that. So this R is here. So this is same as, let's say there are lots of realizations where the value of O is same. Let's say what? Let me call it. So value of OI is X, for example. So there are MX realization or MS realizations where the value is S, right? So I am just grouping it according to the realizations. This is okay, right? Is it clear? So only thing is that summation MS has to be equal to R, because R is the total number of realizations. So now I just put R inside. So what is this object? This is the probability of S in fact, right? This is how you, if you take R going to infinity, this is how you calculate probability in simulation. So that is in fact summation. So this is S, so this is P of S, S. This is what this object is.
So what is this?
S is the, so O will have different values, right? Then you bin them. So let's say for something O is 5, for one realization O is 1, for another realization O is 7. So how many times you get 7? So S is 7, you get MS time. How many times you get 1? Let's say. So S is 1 and you get M1 times. Right? So this is just like, just make it histogram. This is over different realization. So you have one realization. So there is nothing time, no time here. Time, because one realization might mean also a one evaluation over some time.
So your example was that O could be suppose the position after nth. So
yeah, so S can be the O can be the position of a nth step. Xn. So which is the summation of some random variables, right? So this is in fact quite general. It is true for any random processes. Huh? So this yeah. So it says that basically. So what is P in fact? So what is P? It's a distribution. Let's think about the discrete case, right? So if you remember when Constance says P is just the success over the total number of trials, right? So in fact you can make it rigorous because P is just a delta function averaged by delta function. Right? P of S is in fact delta S minus yeah. So P of S is in fact delta of S minus S of, so this is a value and this is a expression in terms of the random value. This is right. So then actually to take the average, so we will just get this. So I'm assuming that they are independent. So because this is how you actually calculate probabilities, right? If you want to calculate, suppose you have to find out what is the distribution of X for a random walk. So this is how you calculate, right? You just take the various tables from random walk and then bring them up and then just divide the success divided by the. Okay, let me just now come to the lecture. So yesterday I did. Do you have any questions from yesterday's session? Maybe no, right? Any questions from yesterday's session?
So while defining that this functional like capital T equal to capital Ux, you wrote Ux greater than equal to 0. There are some questions that is it necessary for the formalism to work?
So it is sort of necessary. Basically, it doesn't have to be greater than 0, but it has to be bounded from below. Because you see that you are taking this Laplace transform, also finally it becomes a potential in that
case you can take Fourier transform.
But then it becomes a different. Yeah, you can do that. Actually, then it doesn't become quite a potential, but it becomes something. Actually, you can do actually. So if this function is not bounded from below, so then you can do Fourier transform. But then this potential in the quantum problem, it's not a potential because there is an eye hanging out in front of the potential. So it's a imaginary potential. Yeah. But the formalism will go through actually. So you cannot just call them that U or V that is a potential. That's it. Yeah. But you can actually do even if it's not. You just take a Fourier transform. In fact, it's a nice problem. Suppose you want to calculate what is the area under a Brownian motion. What is the average area? 0, right? If you just so if you just take start from origin and say go up and down. So this is a positive area and this is a negative area. So it's a 0. So what is the distribution of it? So you can actually calculate this using. So I did this Feynman parts yesterday, and then so I'm not going to write down this again with you. So then I did this Brownian motion with external potential, right? So I had this equation dx dt equal to f of x by gamma plus tau, and so eta is Gaussian white noise with a correlator theta t prime equal to t delta t minus t prime, and then from there I went to the Fokker-Planck equation. So which was Fokker-Planck equation for E of xt, so which was del t equal to minus del x of f of x by gamma t plus d del 2t del x. Okay. And then I said, okay, it's so if you just follow the derivation of this equation, it's actually quite straightforward to generalize for n particle, right? So you just instead of one variable Taylor series, you just take n variable Taylor series, and what you get is a similar equation. So generalize n particle. So what you get is, so then you have a x1, x2, xn variable. So you write down a Copernican equation for this one, and what you get is del T equal to, is quite similar, minus I equal to 1 to n del xi of ai, which may depend on all the coordinates, into t plus half I equal to 1 to n del square del xi. Okay. Let me call it b ij, which again may depend on all variable xi. Okay. This if you just follow the, just do the scalar expansion in variables. Okay. So this is what you get. So now let me just, so I'm going to come back to this one, but let me just give you an example. So so example was m d2x, for example is this, plus gamma dx dt equal to some force f of x plus so there is a slight distinction between this noise and that one, because it's just a prefactor. So if you divide this noise by gamma, you actually get that. So that was the equation you saw in physics class, right? So this is the full Newton's equation plus the noise.
I have a question. So in this Copernican equation, when you are finding out this x average and x square average, why are you only determining from the overlapping?
No, because this is, so the same. So this problem, this Copernican equation corresponds to this Langevin equation. So now I am saying, because I don't know this Langevin equation, so suppose my Langevin equation is this one, the full Langevin equation. So what is the corresponding Copernican equation? So this is what I am just going to write.
Then you just write the x average corresponding to this.
So I will just write x average corresponding to this equation. So this is the Copernican equation for the overdamped Langevin equation, right? So this is, so I'm just going to write down if you have all the terms, the inertia also. So maybe I told at some point of the class, no, there is some process which is Markov and some process which is not Markov, right? So this is a Markov process. In fact, in x, because it just involves the first derivative in x. Okay? So therefore, if you want to know x at some time, you just need the x at the previous time. Because of that, if you want to know probability at some x and t, you just need the probability before. Right? So what is the Markov process? So Markov process so what is the Markov process? So Markov process is, if you want to know t of, let's say, x n t n, given x n minus 1, t n minus 1, x n minus 2, t n minus 2, all the way x1. So the indices are such that this tn is greater than tn minus 1, greater than tn minus 2. Right? So if you want to know this, so this is equal to, in fact, t of xn tn given xn minus 1, tn minus 1. Right? In fact, I use this property to actually derive the Fokker-Planck equation, because when I wrote down this integral equation, in fact, I just wrote down on the right hand side, there was only one term, just the previous step at time t. When I wrote down the equation for, expression for left hand side, it was t plus delta t, on the right hand side, it was just t. So I in fact used this property. And this is easy to see because the evolution equation has only one derivative. Right? So just to find anything, you just need the previous x. But suppose this is not true. Right? If it is not true, then the process is not Markov. And then actually the direction doesn't go through. Right? So in fact, if you look at this, this is not a Markov process in x now, because you have second derivative. Right? So any time when you have a higher derivative, the process is not Markov. But you can make it Markov. So if you just go to one higher dimensional space, so if you go to yeah, in a higher dimensional space. So it's not Markov in x space, but if you just go to xb plane, so it becomes Markov. Yeah. So let's go to xb plane. So what are the equations? So now I have two variables. So I need to write down a Fokker-Planck equation for two variables. My variables are x and t. So what are the equations? So one equation is dx dt equal to v, right? And what is the other equation? dv dt and dv dt equal to minus gamma v plus f of x Now actually if I use this, so I have two variables, if I use these two equations, I can actually find delta x average, delta v average, delta x squared average, delta v squared average, and delta x, delta v. Right? Because these are the 5 quantities I need. So what will be the Fokker-Planck equation for this case? If I write down the Fokker-Planck equation for that problem, what will be del t, which is a function of x, t and t, del t. So this is minus del x of delta x by delta t minus del v of delta v average delta t into t. Then I got the second term, half del square del x square del x whole square plus delta t into t plus half del square delta t square plus t. Then I have one cross term, right? So this cross term will, half will go away because there are two terms. So it will be del square del x del v of delta x delta v average by delta t.
How do you get this? What is the relation between the initial and the final probability densities? The Chapman-Kolmogorov condition for this equation?
So because this equation I wrote down for general and variable, right?
No, I'm asking what is the Chapman-Kolmogorov condition for this? Like you started with the how the initial and the final probability densities were related using the transition probabilities.
Yeah. So when I derived that, so I derived for one variable, then I said that you can generalize to n variable using the same way. This is just do the Taylor-Swift extension. So what are the terms you will get in a Taylor-Swift extension? You will precisely get these terms, right? Because this is just n variable problem. So what is this? So you are asking what is this A's and B's, right? Because this I didn't derive, but I said that this is just a generalization of n variable problem.
No, see, to derive this equation, you must have started with, like in the initial case.
Yeah, it's just the same, Chapman-Kolmogorov
In
equation.
terms of x, v and t, so then you have to do some Taylor expansion with respect to x and v both.
X and V both. So it's like x1 is x and x2 is v. Yeah. So it's like a Taylor expansion in x and v. So these are the terms in fact you will get, right, when you do Taylor expansion in x and v. So I am saying that you don't have to, when you, now my point is that when you are given a problem, you don't have to go to that equation and do the Taylor expansion again and again, because we have done it for n variable problem. Yeah? So you can just identify one variable as x and the other variable as v. So I just n equal to 2. So I am just coming from here to here. Now this actually you can just calculate trivially, right? Because you want to keep terms up to order delta t. So for delta x, what is the term up to delta t? It's just v delta t, right? So therefore, okay, so let me just write it down. So therefore, delta x average by delta t equal to v, right? Yeah. Just put here. So what is this noise correlation? Actually, this noise correlation is not actually this. So what is E prime? So what should be the noise correlation? So this should be actually equal to 2 kBt gamma delta t minus t prime. So it's gamma square t. 2 gamma square t.
No, eta is.
So this is
gamma, right?
so this is a slightly different noise, I think.
Yes.
Because it's just a factor of gamma more there.
Eta is I by gamma, right?
Eta is I by gamma.
There will be another gamma squared.
So now, so I can put a gamma square here and I can put a gamma here. And in fact, this is my diffusion.
So this velocity that you are defining,
Yeah.
one is E, that is the instantaneous velocity.
Yeah.
And the other one is the average velocity, right? You're taking the mean of delta x. Down. Mean of delta x.
This one.
Yeah.
So when delta t is very small,
Yeah. So the velocity using the Langevin equation, dv by dt.
yeah,
So that is instantaneous or the average?
this is instantaneous velocity.
That is the instantaneous.
This is not the instantaneous velocity at time t.
So when if we delta t equals to 0, it becomes instantaneous.
It's an instantaneous velocity because this is, suppose you are doing a simulation. Dx dt equal to v. V might be a function of time. So how do you do it? You just make your delta t very small, find out the velocity and just find delta x, right? V into delta t. So just think of evaluating these two, doing a simulation of these two equations. So you have x and v and then go to x at t plus delta t and v at t plus delta t using these two equations. So
that's why.
Okay, yeah. Maybe let me. Maybe I'll just.
Sir,
Yeah,
that equation, that Langevin equation is the overall limit of this. So why should we now solve it into this?
No, because actually no, it's the same actually. So.
Oh, this is the gamma part.
So maybe.
Oh, okay.
So that's the. So when I put in eta, so because so eta that correlation is 2d delta t and this.
I think there should be an extra gamma square.
No.
Oh, yeah.
dv by gamma is v.
So this is in fact.
Earlier correlation was 2d delta.
Xi of t prime is 2d by 2d gamma square delta t minus. Right?
Yes, yes.
It's okay. Now it's fine. So now, how am I going to emulate this thing? So dx dt. Okay? So therefore, delta x is equal to d delta up to order delta, right? So therefore, delta x average is also b delta.